In this section, I'm going to describe to you how I collected the data that you are going to see in the capstone file. This is data that verifies Newton's second law. We're going to use a modified Atwood's machine to do this. Atwood's machines are something you can look up on Wikipedia. You don't really need to know what an Atwood's machine is. It's simply a device for working with gravity. A modified Atwood's machine is different in that in an Atwood's machine there would be two masses on two different pulleys, both free to move in the y direction. Here we're not doing that. A modified Atwood's machine has a track which is horizontal. So the cart that's on the track is moving horizontally, and the normal force is just simply equal to the weight of the cart. There is no component of the acceleration due to gravity in the horizontal. So this motion is due entirely to the mass that's hanging over in the other corner there. You can see it hanging from the pulley. The string is very light, probably doesn't add anything to the uncertainty here. The pulley rotating probably does add something to the loss of energy of this system, but it's going to be negligible compared to the other parts. What's going to happen is I'm going to put a mass on that hook. I'm running the string from this hook through the bar and over the pulley. I've set it up so that the string is not rubbing anywhere, so there's no friction. I'm going to put the cart down like this, and I'm going to hold it. I'm going to take the pressure off of the force sensor that's built into the end of this. This hook is attached to a force sensor. I'm going to take the pressure off, and I'm going to start capstone. At that point, it should set 0. If it doesn't, I can set it to 0. I'm then going to put the pressure back on and let the string go. And now the force is going to jump up, and we have a static situation just like we had with coplanar forces. The tension of the string is simply equal to the weight of the mass, the hanging mass. Then I'm going to let go. That's a critical point. That's a point you have to identify when you're taking your data out of this, you're doing your analysis. When I let go, this becomes a dynamic situation. The sum of the forces is not 0. It's equal to some force that we don't know. But we're going to measure its acceleration by letting go and watching the cart accelerate. The cart has built into the wheels a rotary encoder so that it can measure how fast it's moving. And I'm going to record the velocity of this cart. And if I give you a velocity curve, you can find the acceleration. So that gives you the acceleration of the cart. You already know what drives the acceleration, the force of tension. The only thing opposing it is friction. Now, friction is significant here. So what I've done is, remember in the first lab, when we had uncertainty due to the instruments, we could do nothing but improve our instruments. But in the pendulum lab, we looked at the parameters and found that if we increased the length significantly of the string, then that would reduce the uncertainty. Here I'm going to do something similar to that. Since we're only interested in the motion in the positive x direction, and friction is always going to be at the back, if I raise the back end of this and give it a small component of g sine theta in the positive direction that equals the friction, I will reduce the friction. Now, it's not perfect because the friction of the cart, rolling friction, whatever it is, the loss of energy is not linear. It's worse at lower speeds than it is at higher speeds. But it will help. And I'm going to just talk to you about that when we're looking at the capstone file. And that's it for this section. That's all I do. I'm going to do it 8 times with 8 different masses, and you'll see in Capstone how that works out. So this is the section of the video that covers Capstone and the data, but I wanted to start here and show you how I set this up. This is Capstone when you first open it with no experiment logged in. Plenty of controls. Again, we're not going to be needing most of them this time around, but I'm going to show you what we do need. The first thing we have to do is connect our cart. So we go to Hardware Setup, click on it, and you see the little Bluetooth is working. My cart, let me actually show you. My cart has electronics inside, charge port, another port for something else I don't remember, and an on button. If I press the on button, I get flashing red light, and the Bluetooth lights up. So now it's trying to pair with Capstone. So I go back to Capstone, and here it is. That's the cart I just tried to pair. I click, and it's connecting. And we wait for a couple of seconds. Doesn't take that long usually. Hopefully, there we go. And we have several options here. We have the Smart Cart Position Sensor, which is also going to be used to measure velocity. That's the rotary encoder in the wheels that I told you about. The Smart Cart Force Sensor, which is the hook, well, not the hook, but inside the cart, and it's connected to the hook. And we're going to be using that to get the force. It also has an accelerometer and a gyroscope, but we're not going to use those. And I'm going to turn them off. And that's it. So I click on hardware to get rid of this. Now we need a couple of graphs. I'm going to click and drag down till I see that its bottom half of the screen is lit up. I'm going to do the same thing for the top half of the screen. And here it says set measurement. Capstone doesn't know what you want to do because there's a lot of choices. And if I click on here, you'll see some of them. This is where I want the force. I click on the Smart Cart Force Sensor. It tells me the force in newtons over time, which is exactly what we want. I go over here, and I want the velocity in meters per second, also over time, and that's exactly what it's given us. And we're ready to go. So let me again demonstrate for you. We need this one. And I go back to Capstone. I come down to the corner of Capstone that you can no longer see, and I click record. And it begins collecting data. You can see that the force sensor is reading 0, the velocity sensor is reading 0. If I then just give it a little nudge, get off, it goes down there. And the force sensor, of course, stays at 0 because I didn't do anything. But if I pull on this, I get a positive force. And there you go. So that's how data is collected. Now, ours is going to be a little more organized. Let's press stop. And we'll go back to here. And let's now go to our data file. Recent experiments. Newton's law. Discard this. And there we have the, this is called the energy loss run. I just want to make sure we're still recording the right thing, and we are. The force doesn't matter here because we didn't measure anything with the force. This is the cart running without the string attached. What you see, this little bump here and here is just me playing around. When this kicked off, the spring leapt up with to give you velocity. Then you get a little jar here, and when it crashed into the barrier, you get a little force because the force meter's attached to the hook crashed. We ignored the force. What I want to look at is this. This is a velocity curve. So this is me trying to get this thing organized, holding it still, velocity is 0, and then there's a little spring in the back. I click on that spring, open it up, and it explodes into motion. it jumps up and now has a constant velocity. Once the spring is fully extended, it's not accelerating the unit anymore, and we have a constant velocity. At some point, it reaches the end of the track, crashes into the barrier, and stops. Now, the reason I wanted to show you this is because I wanted to talk about the uncertainty here and this velocity, how much we lose over this couple of seconds. When I did this, I've already mentioned that I raised the back of the track so that we have a component g sine theta that is equal to the loss due to friction's various sources. And this is what I get now. It's almost horizontal, not quite. Of course, that doesn't mean anything here. So let's actually plot this thing. I'll need to highlight those points. There we go. And you can see that I have a slope of 0.0109, plus or minus a number that's so close to zero it might as well be zero. So there's still some loss, but it's a very small loss. It's certainly small compared to the accelerations we're going to be measuring. In fact, I'm going to declare it almost negligible. However, we're going to use it to set our uncertainty. An easier way to do that, I guess, would be this. This is the maximum, this is the minimum, and why don't I have the mean? I should have the mean. Somewhere I should have the mean. Isn't that interesting? Well, there it is, the mean. Get out here. So the mean is 0.827. That's the mean velocity in meters per second. It's 0.827. The max is 0.835. The min is 0.811. Now, those are the extreme edges of the loss over the 2 seconds. And I think we can decide to accept that as our uncertainty. The CART's uncertainty, the force meter, they're all to within millimeters per second and millinewtons. However, if we look at this, the mean is 8.27, this is about 10 high, this is about 15 down, add a little to be safe, round it up, and we can set our uncertainty to 0.802. Is that right? Yes, 0.02. So in this case, the velocity is 0.827 plus or minus 0.02 millimeters per second. And that's the what you're going to use when you're doing the calculations. The force sensor you can use to 10 to the minus, sorry, not 10 to the minus, 0.005. We'll use that, 0.005. And let me actually, okay, so we're ready to move on to the next one. So here's an actual data set. See, I've named them all, trial 1, and I put in the mass in grams. Not that you really care for this one. I'll explain why. I'll do the same thing down here. You use a little drive symbol, click down, click on trial 1. And here we have clearly meters per second as a velocity. This thing is, well, the little joggling here is me trying to hold it steady, and then I let it go. And then the force due to the mass on the other end of the string, the tension in the string, causes it to accelerate. The velocity is changing, that's an acceleration. At some point it crashes into the barrier and it's all over. Now we're going to want to measure when it's smoothly accelerating. So to do that, we're going to have to highlight the points. We click on this, come up here, grab this, come down like this. I don't want to get too close to this little curvy thing up here. That's where it's be misbehaving because of the barrier, and you know, I'm not sure where exactly I let go, so we'll skip that. And then we'll do a fit. A linear fit. It's already a linear fit. Why won't it work? There we go. A linear fit. And we have, since this is a velocity curve and we just measure the slope, it's 0.519. Plus or minus some number so small, it might as well be 0. So that's our acceleration for this run. Now, we have to get the tension. And there's a little bit of a problem. So let me bring this down so it doesn't look so jagged. What happened here is, and let me get one of these so I can demonstrate. So what happened here is, when I pressed record, I was holding the cart still, and I had not put the string on. So this is 0. And if I do the mean, I get 0. Just as it should be. Then, once I'm sure this is 0, I release the string onto the hook. And now I'm getting a mean of 0.14. I'll probably add another digit to this before you, not probably, I will add another digit, just to be sure we're safe. And that's the mean force here. But this is the static situation. This is not moving. I'm still holding the cart still. And the mass hanging is what's putting the force on the hook and reading this. So this is a static situation, just like last week in Coplater forces. Sum of the forces is equal to 0, and the only force is the tension. Tension is mg for m hanging. But that's not what we want. What we want to know is when this thing is moving. At some point along this curve, I released it, and it started to accelerate. And now it's not a static situation anymore. The sum of the forces is not 0. It's accelerating. So the sum of the forces is some unknown force. And we want to measure its acceleration. To do this, we'll have to use time. In later runs, you'll see that there's a significant, if I actually switch to, say, the last one, you see that there's a significant difference. So there is an obvious change here that you can't miss, but here, that's not clear. So what we can do is, we can do it by time. This, I start, about 2.2 seconds, and I go to 3.6. So I try to do the same thing here. 2.2-ish and 3.6-ish. And there I have a mean of 0.14. That's the force we're going to use, because that's the force that accelerates the cart down the track. You have to do this 8 times. Well, 7 now, I guess, because I just did it for you. Actually, you should do it to 8 because I will add another digit to the mean force. And once you've done that, you'll have 2 columns. One for the tension in the string, and one for the acceleration of the cart. So that's the acceleration of the force that we want. So that's the A of MA, when the sum of the forces is now equal to MA. You're going to plot this, and from the slope, you'll get that mass, which is, of course, should be the cart. In order to know what to plot, you're going to have to do free body diagrams. And we have 2 objects here, so you have to do 2 free body diagrams. One for the hanging mass, one for the cart. You have to draw all of the forces. Normal, weight, tension, and friction. So there's friction force is kind of odd here. It's not contact friction like we would normally see, but it's always a loss. So that force is always back It acts like a force that's acting in the opposite direction. So that has to go on the free body diagram. And the other body, of course, just has the tension straight up and mg straight down. And then you're going to plot the tension and the acceleration and verify it with the mass. And I'll explain that in the Google Doc. And that's it for now.